In education, a prototype is a contextual example that fits a particular schemata. A good prototype becomes an external resource that students can use to scaffold their own problem solving. The more prototypes a student has access to, the more likely they are able to transfer the knowledge from one context to another. I'm Ben Dickens, and today I'd like to talk to you about how to build quality prototypes with students. Prototypes that can reduce students' cognitive load, enabling access to composite tasks that will self-fade as our students transition from being novices to experts. First, let's think about what we already know about learning and consider some of the barriers our students face when encountering complex concepts. Sweller said that learning is defined as an alteration in the long-term memory. If nothing has been altered in the long-term memory, then nothing has been learned. This definition underpins the growing body of research behind cognitive load theory. For our purposes today, we'll consider the simplified model of the core elements of the theory. Students process information in their limited working memory to store knowledge in their unlimited long-term memory. If this process is successful, then the student has learned something. This information can then be recalled and applied over and over again. Barriers to this process are when the working memory is overloaded and cannot process the new knowledge into the long-term memory. This is especially important when considering transient information, like something a teacher says or shows to a student. If a student needs to retain that information in the working memory to be able to access problems in the rest of the lesson, the student's cognitive load will be too high and successful learning is unable to happen. A prototype is a way of building a resource that stores transient information from a lesson in such a way that students can refer back to it as an aid while solving problems, later freeing up slots in their working memory. Prototypes should make use of dual coding theory, using the physical layout of information and diagrams to aid explanations clearly. So, what is the difference between a prototype and a worked example? If the worked example is clear, concise, and loaded with enough information that students could use it to solve further problems, then very little. In physics, we often require students to complete composite tasks. These are tasks that are made of several smaller components. Each component represents either a piece of knowledge or a skill that is required as part of the composite. Simple worked examples often address individual components and therefore have a vital role in learning. A prototype, however, should be able to reflect a composite task, drawing in the elements from each component and demonstrating for students how each part contributes to the whole. My first example of a prototype that I use in lesson is my motion graphs prototype. There's always been a debate about how to teach motion graphs to students, and it's not a debate I'll be able to weigh in on this video. However, I do believe that starting with a clear prototype alleviates a lot of the confusion further down the road. I use a visualizer in lesson, and together as a class we draw a motion graph representing a journey of a random object. You could draw this on a whiteboard or use a graphics tablet to beam it straight to the screen that the students are seeing it on. For the purposes of my distance learning, I have taken a picture of some graph paper and I've done a screen recording of my iPad as I produce the diagram. We start with the axes, ensuring students label X and Y correctly. Even though this prototype won't represent a real journey, we will include our axis labels and units. This provides a concrete example students can check back with as they produce their own later. I'll also include values to my x-axis and my y-axis in order to use later when discussing gradients. I then model 3 common lines students find on a motion graph, specifically here distance time graph. We then go through each line individually, adding annotations to describe what they look like and what they represent. The use of colour to differentiate each line is useful for students to return to and pick up the part of the graph that they need. Once we've discussed each of the 3 lines, we can then also include information regarding the gradient of the line. Pedagogically, you would want to ensure that you're introducing these ideas to your students at the appropriate time for your curriculum, and you may want to add this information to your prototype at a later date. This prototype is now complete, containing all of the components that involved in motion graphs, recognizing familiar shapes, inferring physically what they represent, basic graph plotting, reading skills, gradient calculations, and understanding of rates. Together, these components make up the composite tasks students are expected to be able to complete. With the addition of a component on balanced forces, weight, and air resistance, this prototype could be used later to support a more complex composite in a terminal velocity problem. My second example of a prototype that I use frequently is the refraction and reflection required practical diagram. Students often have difficulties when completing this relatively simple practical. This is often because what seems very simple, shining a beam of light through a glass block and measuring the change in direction, is actually a complex composite of knowledge and skills, combined often with transient procedural information that is required to be able to access any of the results. When introducing this investigation to students, I ensure that we start with a clear, concise prototype to refer back to as they're doing the practical work. Again, I start with a diagram that the students and I build together. It's important here to note that this does not have to be dictated to students in true lecture style, but should be the result of meaningful questioning, allowing students to truly contribute to the prototype. This prototype is loaded with procedural information, including the basic steps. It also is an opportunity to embed the expectations of the investigation. You should include what we expect to see, both with the angle of refraction and the angle of reflection. Discovery practical work is rife with issues, as students tend to learn fantastically well the misconceptions that they discover themselves. A better approach is to front-load students with theory, provide access to the prototype so that the investigation is impactful and produces the outcomes we desire. Whilst there is definitely a place for discovery learning and engagement, it does not ensure students store the correct knowledge in their long-term memory and therefore should be deployed carefully. A good prototype is contextual and fits into a particular schemata. The schemata is the interconnected web of pieces of knowledge that makes up the student's understanding of a subject. The more links between pieces of knowledge, the easier retrieval is for students. As a schemata grows, the web gets wider and wider, and what is needed is a tool for students to bridge the gaps between certain ideas. The prototype, shown in blue, should fit neatly into the schemata and facilitate links between different pieces of information. The prototypes have a built-in redundancy, which are closely linked to the cognitive load theory concept of guidance fading effect. Essentially, as learners acquire more knowledge and therefore expertise, they'll no longer need to refer back to the prototype as often to solve problems. Eventually, the prototype has been firmly transferred into their long-term memory, and the physical versions, being drawn on the whiteboard, become redundant. So, let's summarise. Prototypes reduce students' cognitive load. Students can free their working memory of the unnecessary load early in learning and concentrate on applying the knowledge and rehearsing the processes to later store in long-term memory. Prototypes must be clear, concise. They need to contain specialist language, but they must be explained and accessible for students to be able to use as scaffolds. Good prototypes collect together the transient information in a topic, freeing up space in the student's working memory. And finally, good prototypes are made redundant as students rehearse and practice. They should transition their prototypes into their growing schemata. Thanks for joining today. I hope you found something useful. Any questions, please do not hesitate to contact me on Twitter at Mr. B. Dickens, and I hope you enjoy the rest of Chat Physics Live 2021. Goodbye.